Hi. This is a new setting. I'm going to have to talk a little bit quieter because there are people here. And in Unit 6, we are going to add to our synthesis toolbox. And we're going to look at a set of reactions called radical reactions. And there's going to be some new terminology, some new formatting, actually, because radicals, we are mainly moving one electron per arrow, which is a little strange. Because in the alkene reactions we're always moving either a pi bond or a lone pair, which are both cases 2 electrons. We'll take a look at all of this terminology and why we use what's called a fishhook arrow. And hopefully we should be able to get all the way to not only talk about the generalities of this reaction, but look at specifically the mechanism and the regio and stereoselectivity. Alright, Unit 6, 06B20, radical halogenation. What is a radical? A radical is a molecule or atom that has an unpaired electron. And an example of an atom that is like that is, we'll see bromine. The bromine radical has 3 lone pairs and 1 unpaired electron. The thing is, if you use our formal charge equation, formal charge equals the number of valence electrons for bromine is 7 minus, and I say sticks plus balls. Sticks meaning bonds, but there are no bonds, and there are 7 balls. Sticks plus balls. So that's neutral. Most radicals that we are going to see are going to be neutral. It doesn't have to be a single atom, it could be a molecule. And the molecule that was on that cover sheet was this radical here, an unpaired electron on this carbon. Now we'll learn more about radicals on carbon, or unpaired electrons on carbon. This carbon has 1 hydrogen. Okay. And how do I want to draw that? Like I'll draw it down this way. So if you use the formal charge equation again, it's carbon has 4 valence electrons minus 3 sticks plus 1 ball. That's also neutral. So both of these are radicals. Now, how do we form a radical? Forming a radical is fairly straightforward. We're going to impinge the molecule with some energy, and we're going to get what's called a homolytic bond cleavage. Homolytic bond cleavage. And let's use hydrogen peroxide. Hydrogen peroxide looks like this. It's H2O2. Weird looking molecule. I'll put in all the lone pairs, and we impinge this with either light or heat. So heat would be a triangle. So this is triangle equals heat. Okay. Or if we're going to use light, it's the symbol is H nu, the Greek letter nu. It's Planck's constant times frequency. Why do they do that? Because if you remember your general chemistry, the energy of a photon of light equals H nu. Okay. But we'll just use Planck's constant times frequency. So either heat or that symbol. And homolytic means that each atom of the bond gets 1 electron. So look how I'm going to do this. I take 1 electron from the bond and I put it directly onto the oxygen on the left, 1 electron from the bond and put it on the oxygen on the right. We're using what's called a fishhook, because we're only moving 1 electron per arrow. You see how it's like a little barb? It's not a full arrow with, that has 2 lines. It only has 1 line, almost looking like a fishhook. And that's what a homolytic bond cleavage is. 1 electron in the bond goes to each of the 2 atoms. What is our result? Our result is this. We have 2 molecules of HO radical. You could use the formal charge equation. This is 6 minus 1 plus 5. Okay, neutral. So again, another neutral radical. The opposite of homolytic is heterolytic. And we've seen heterolytic before. Heterolytic is you move 2 electrons. So for instance, in our alkene reactions, we have this. I'm going to use a full arrow now. Okay. A full arrow because I'm moving both 2 electrons of the pi bond, and over here transferring 2 electrons of this sigma bond. So that's called heterolytic bond cleavage. Okay, we're not quite yet ready to look at our first reaction, which is again going to be named radical halogenation, because I want to briefly talk about radical stability. And we're going to look at a carbon radical. So if I have, I'm going to draw out the carbons and the hydrogens. Okay. If I'm going to make this a radical, what I want to do is I want to do a homolytic bond cleavage on this bond right here. Okay, I know this looks a little strange, and actually this doesn't really happen, but I'm forcing my drawing to give us a radical carbon. Okay, so there are a couple things, and we have an H, a hydrogen with 1 electron, but I'm more focused on the radical carb. The thing about this is that we are going to assign a hybridization to this carbon, and the hybridization we're going to assign is sp2, which is a little bit strange because if you think about the number of areas of electron density, you would say that it has 4 areas of electron density, and this would be sp3. But let me show you the orbitals when this is sp2. You know that if it's sp2, you have an sp2 orbital maybe to the right, an sp2 orbital towards us, and an sp2 orbital away from us. Okay. So I'm not actually drawing the lobes like you may be used to, right? The lobes that signify the sp2 orbitals. I'm not literally drawing the bonds. But if this is sp2, you know that sp2 always comes with an unhybridized p orbital. So again, we're going to assume that this is sp2, and because of that, we have an unhybridized p orbital. That's where the radical goes. That's where the unpaired electron goes. You could think about, well, if this was, if there was a lone pair here, 2 electrons would go in the p orbital. Okay. It gets a little bit hairy because a carbanion could be either sp3 or sp2. Let's not worry about that. I'll tell you now that all the radicals, all the carbon radicals that we'll see are going to be sp2 hybridized. Okay. What is the consequence of this? The consequence of this is that the geometry is trigonoplanar. And when we first talked about reactions, the alkene reactions, you know, a double bond is trigonoplanar. A carbocation is trigonoplanar. And what do we see? We can see attack from either side equally. So just like we saw racemic mixtures with alkene reactions, it's likely that we're going to see racemic mixtures for radical reactions if we form a chiral carbon. Okay. I just wanted to point out that geometry because it's going to be important when we talk about stereoselectivity. The other thing is that it follows the stability of carbocations. Tertiary greater than secondary, greater than primary. In this video, we're not going to talk about allylic radicals, but we will definitely later on in the unit. Okay, so again, just like carbocations, radicals follow the same stability trend. Now we're ready for our reaction. Radical halogenation. If you're taking notes in class, you could put a notation here. I like to put, if it's our first reaction 6A, right, for unit 6, reaction A. But I'm not going to do that here. But you should, if this is the first radical reaction that you're going over. And I already messed up. The name of this reaction is radical halogenation. Okay, on the cover sheet I said of an alkane, but that's only because I want to differentiate it from all of those alkene reactions that you have studied previously. So take a look at the type of alkane I'm using. Okay, it's a branched alkane, and I purposely did this because there are several types of carbons: primary, secondary, tertiary, and even we have a quaternary carbon. Okay. The reagents for radical halogenation is going to be Br2, almost always bromine, and I'll go over that why in just a bit, and light or heat. And for my class, I only want to draw the one major product, and that is you want to mentally remove the hydrogen that gives you the most stable radical, and then put the Br there. So there's no hydrogen on this quaternary, so we can't put the Br here because we have to replace a hydrogen. We're going to remove this hydrogen that's on the tertiary and put the Br right there. Now if you listen carefully, I said we're going through a radical intermediate. Well, the radical intermediate is trigonoplanar, so that Br could come from the front or back. But I notice here that this carbon is not chiral. Okay? So that you should not put any wedges and dashes on this carbon. This is interesting. If I show you a simpler alkane like this, and then I do my Br2, and I'll use heat this time, what I notice here is that whether I put the Br on this carbon, the second carbon, or the one next to it, I get the same products. Okay, so I'm just going to choose this one right here. Okay. What I notice in this case, my hair. What I notice in this case is that we created a chiral carbon. So in actuality, because there's a radical here, and we'll go through the mechanism in just a bit, that bromine could have come from the front or back. So really, my final answer would be this. Because I am, and most professors and most people who are interested in mechanisms, they're really interested in how many products do you get. If you just draw this and you assume there's only one product, that's actually wrong. You get two products that are enantiomers of each other. When you have a product mixture, that's a 50-50 mixture of R and S, or 50-50 mixture of enantiomers, you get something that's racemic. Let me circle the final answers for both of these problems. Okay. So no wedge dash here because none of that carbon that we worked on is not chiral, but this one is, that one is. Okay. Let me go through the mechanism. So the mechanism formatting is odd. I think it's odd. So the warning is format is odd. Okay. Because I like to draw my mechanisms like a snake. One continuous line that weaves in and out. Mechanisms for radical reactions typically go line by line, like you're reading a paragraph in a book. I'll show you this, what I mean. Okay. So far, that's what we have so far for radical halogenation. Maybe, honestly, let me put here some of the key points. Like the regioselectivity and stereoselectivity. Regio means that you're choosing a constitutional isomer or a set of constitutional isomers over another set. So you notice that I didn't make any constitutional isomers. I didn't put the Br here. I didn't put the Br on a primary carbon. That's what I mean by we chose this one. So we should say here the regioselectivity is, let's say we replace hydrogen on most substituted carbon. Okay, and any carbon is up for grabs. Okay, it's not like the alkane where we have to focus on the double bond. You could pick any carbon and ask yourself, if I take off the hydrogen, am I going to get a very stable radical? Or you could say just replace a hydrogen on the most substituted carbon. You notice that this carbon here has no hydrogen, so you can't put the bromine there. So that's regio. Stereo, it's non-stereoselective. Because the incoming halogen can come in 50-50 from either side, front or back, up or down. Okay, so it's non-stereoselective. And we could discuss the non-stereoselectivity and even the regioselectivity in the mechanism. Okay, so I warned you, this is going to be a little bit odd because for radical halogenation and most radical mechanisms, you want to name the steps. The first step is called initiation. So initiation, we're going to take the Br. You don't have to draw the lone pairs at this point. I did ask my students to draw all the lone pairs for the first exam. Homolytic bond cleavage by using what? Let's use light. You don't have to write 2Br. Well, some people do that, but I'll go ahead and write that. Plus, so when you write or draw a radical with its electrons, either you could just draw the unpaired electron, or you could draw all the electrons, all the valence electrons. So it doesn't matter which way you draw this. It doesn't even matter to me whether you draw 2 or not. It doesn't matter. They're essentially the same radical, just drawn differently. That's it. Propagation. please remember this for propagation. It's between a radical plus a non-radical. Okay. Propagation is not two radicals coming together, which is very tempting, and you'll see why in just a bit. There's always a small percentage of people who do the propagation wrong because they don't remember this rule right here, radical plus non-radical. So let's use actually the butane example, and the most substituted carbon is going to be the secondary carbon. Okay, there's no tertiary here, so we're going to go for a secondary carbon. We're going to take the bromine radical that we initially made from the initiation, and this is where it gets even stranger. We are going to meet in space two electrons to make a bond. So I'm going to take one electron from this carbon-hydrogen bond and put a fishhook, okay, somewhere in space. Take this radical, unpaired electron, and draw a fishhook here. Essentially what I'm telling you is I'm going to make a HBr molecule. I'm always slouching. Okay, let me try this. Okay, but there's an electron here, part of the bond, that's kind of in no man's land. So we got to put it on directly onto the carbon. You have to show that. And we have this. So there's a radical. You should know that that other hydrogen is still there, plus HBr. For this mechanism, there are two propagation steps. Again, radical plus non-radical. And you notice that I'm redrawing the product now as the reactant. So again, the mechanism is each step has its own line, whereas for the alkene mechanisms, we typically just draw a pathway that snakes to the right and then to the left. Okay. Non-radical. My non-radical is this, which is going to be a little bit odd to some of you, because you may say, I thought we took care of this Br2 in the initiation. The thing about initiation is you don't want to create a lot of radicals, so you just pulse the solution temporarily with light or heat and get a couple radicals to start the propagation going. So you're not reacting all 100% of the Br2. I mean, you might just be reacting maybe 1%, because all we need is a little bit of this radical just to get the process going. Okay, so I'm not sure if you want to write that or how we can write that. Yeah, I mean, we could just, as a reminder, we could put temporary, okay, just a pulse, because we need actually most of the Br2 to remain Br2. And we get this. Again, meet in space. It's going to take a little bit of practice to make it look nice. And then look what happens here. We created another Br radical. This is our product already, right there. See, an electron here, an electron there, brings a Br over. And you have two electrons now to make the bond, plus Br radical. Propagation. It goes over and over, or it goes on and on and on and on and on. See, this Br now can do what? It could propagate another alkane. Right there. Okay. This step right here is called hydrogen abstraction. I should have wrote that previously. Hydrogen abstraction. To make what? To make the stable radical. So there's most of your product here. Especially if you control the amount of radicals, this could go on and on and on until you take care of all of the alkanes. Now, what would be very tempting actually is to combine these two, right? Because to most people, that seems like the most obvious way to make my product. And that's correct, that could happen. So termination is between two radicals. So the two bromine radicals can recombine. Again, meet in space, and to get Br2. But also we could get these two radicals to recombine, or to combine. And that looks great, right? Because we make the product. And sure, that is great. It's another way to get the product. But the thing is, if we have a lot of radicals swimming in the solution, we're going to get significant amounts of this product, which honestly doesn't really help matters. Okay, it's actually kind of rare to make what we're about to make here. So think about what we're combining. We're combining these two carbons. So I could draw one of the chains, draw a bond, okay, to maybe this carbon here, and we notice that that carbon is connected to 3 other carbons. Okay, 4 carbons plus 4 carbons equals 8 carbons. This is no good. You know, at least for this one, we can add more light, and it's useful. This one is the product, so that's useful. Okay, and this one is really just useless. There's nothing much we could do with this except more halogenation, which, you know, if we're trying to have a controlled reaction, most likely what you're trying to make is this. Okay. So this is essentially useless. We can't break it up. We can't reuse it. It doesn't get us anywhere close to the actual product that we want. Okay. Alright, so that's the mechanism. Again, let me draw you, I have a little bit of time, let me draw you that radical and why this bromine can come in, technically this bromine can come in front or back to give us what's called a racemic mixture. Because I'm going to copy this radical here. We have a bond to carbon, we have a bond to hydrogen, we have another bond to carbon. Okay. And then this is actually an ethyl group. You see where I'm getting that from? This center carbon right there. And we have this. So the thing is, and it doesn't matter where you put the top lobe or bottom lobe, the thing is, when we do the propagation step, right, this VR step here, when that unpaired electron, right, meets in space, okay, that could have met on the top lobe or it could have met on the bottom lobe. That's where I get the front and back. That's where you get the 50-50 mixture. Okay. Alright, let me see if I'm missing anything really important. Oh, yeah. A couple things. We can't use chlorine, okay, to do chlorination because it's promiscuous. It's not selective. So if we have something like this and we use chlorine, we heat, we're going to get not only the product that we would predict for bromine, plus we'd get some of the chlorine on the primary carbon. Okay, and it gives us a bad mixture. So it's not controllable. F2, it's too exothermic. It's too reactive. Okay, it will create a lot of heat. I think I've read stuff where it could cause an explosion. And I2 is too unreactive. Okay. So when we do radical halogenation, we should always use Br2, and you're going to add the Br. Actually, you're going to replace the hydrogen on the most substituted carbon, and that's what I have. Oops, sorry, right here, the regioselectivity. Replace the hydrogen on the most substituted carbon. Okay, that's our first reaction for radical reactions.